Good afternoon. Let's get started. I'm Mark Reinhold. This is Alan Bateman. We are here to talk about modular development with JDK 9. So first, we always like to start off with a poll. Alan has his favorite poll questions. I have mine. My first one is actually, how many of you are here just because you couldn't get into Venkat's talk?
I don't see any hands.
No? Well, okay, I guess that's reassuring. Our egos are boosted.
Oh no, this is the audience that didn't try to get into Venkat's talk.
Oh, maybe that's it. They knew better. So let's see. How many people have tried JDK 9 EA download builds? Okay, a few. How many have tried the Jigsaw-specific ones, which are quite a bit ahead? Anybody? One? One. Brave soul. How many people are running, let's see, Java 8 in production? How many people are running Java 7 in production? How many people are running 6 in production? Ooh. How many people are running 5 in production? Oh! 4? 9? You're not supposed to do that. What else can we ask?
That's enough for now.
That's enough for now? Okay. So we have a ton of material. The abstract for this session was fairly specific, but we don't really feel bound by that. It's a tutorial. We're here to do what you want. Well, at least what you want of what we are able to provide. So we have 4 prepared presentations, and the idea is we pick some subset of these and we go through them at a measured pace with interactive Q&A. You can ask questions along the way. Sometimes we might defer you to a later slide or even a later talk. Sometimes we won't. The 4 that we have are Prepare for JDK 9, which is actually not much about the module system, although it does cover some of the impacts of the module system. We also discuss other changes in 9, other changes that might affect existing code. It's not a survey of all the snazzy new features in 9 besides the module system. We have Introduction to Modular Development and Advanced Modular Development, which are pretty much de rigueur. We will do those 2 here almost certainly. We certainly won't do Advanced without Intro because it wouldn't make sense. And then Project Jigsaw under the hood goes into sort of the science of the module system, the theory behind access control and how it all works. So that's a bit more advanced. So our question to you is, where should we start? Should we do Prepare? Should we skip Prepare? If you saw Prepare last year, it's not that different this year. We're not doing Prepare as a regular session. We are doing the other 3 as regular sessions later this week. So who would like to hear Prepare? Okay, who would really not like to hear Prepare? Okay, I guess you can take a nap or step outside or whatever. Sorry, read Twitter. Okay, so it sounds like we'll do Prepare.
That's fine.
We'll do Intro and Advance. We'll see how far we get. If there's still time, maybe we do Under the Hood, or you can always come to the Under the Hood session on whichever day it is this week. I forget. Okay. Thursday. Thank you.
Okay.
All right.
I will get these.
Leave it to you.
I will get the Prepare talk ready. I have to prepare the Prepare talk.
Prepare the Prepare talk. Yes.
Okay, here we go. So this talk is Prepare for JDK 9, and as Mark said, this is not a talk about all the features in JDK 9. I don't know, maybe Mark, tomorrow at your keynote you might show a big list of all the features in JDK 9. You might, okay. So that would be a good place to hear about, at least get the list of everything that's in there. Instead, what this talk is about is the disruptive changes that are in JDK 9. Some of these are motivated by the module system, some of them are not. But moving from 7 and 8 to 9 is going to be a bit more difficult compared to other releases. So this talk is about some of the incompatible changes that are in 9, as some of them are motivated by the module system, and I just want to talk about what the impact of those is. So when Mark polled the audience earlier on, there were very few hands went up for those that were actually trying out the JDK 9 builds. Can I just ask one more poll? How many people here are concerned that JDK 9 might cause them problems when they attempt to move from 7, 8, and I guess there's someone 6 and 5 as well. When you migrate to 9, it may break some of your existing code. Okay, there's quite a few hands. So good, then this is the right talk for that, because this is what we want to do is talk about some of the things that are happening in 9, why they're happening, and what we can do to work around them. So before I get into that, I have a couple of little background slides. These might be a little bit boring before I get into the meat of the talk, but they're just to give you a bit of a background as to what's going on. So the first thing is what are the high-level goals for JDK 9 and Project Jigsaw? And we can list them down maybe as 4 goals. Number 1 is to make the Java SE platform more flexible and scalable. This is about being able to create reliable, compact deployments that you can use in the cloud or use in small devices. It's about improving the overall security and maintainability of the core platform and also for libraries. When we get into the module system, you'll see that we're actually encapsulating a lot of security-sensitive APIs within module boundaries. We're also encapsulating a lot of other JDK internals, which is very good for overall maintainability. It's great for those that are actually working on the JDK because we don't have to be too concerned about code that's making use of JDK internals. It's also good for library and application developers because if they can't get at JDK internals, either knowingly or unknowingly, it'll improve the overall maintainability of their code as well. It's about making it easy to construct, maintain, deploy, and upgrade large applications. This includes Java SE and the EE platforms eventually. And partly escape jar hell, and you'll see a little bit about that as we go through the slides today. Also, what we're doing is setting the groundwork for enabling a whole bunch of future performance enhancements. So that will be quite interesting. You'll see some of the J-Link stuff today, and there's more to come. Just a bit about the categories of APIs in the JDK today. We can loosely split them into supported and unsupported. When you use a java.star API, as in Java Lang or Java IO or Java Net, then you're using a JCP or a standard API. Similarly with JavaX. These are all part of standard supported APIs. The JDK has always shipped with a bunch of what we call JDK-specific APIs. For a long time, we were creating these JDK-specific APIs in the ComSun namespace. But there's also a whole bunch of other JDK internals that are in the ComSun namespace. And this has been a very confusing point for many, many years. I know if I listed out a whole bunch of ComSun APIs, I'll guess that most people won't know whether they're supported and documented APIs versus those that are internal to the JDK. So there's always been confusion around the ComSun APIs. In the last couple of years, we've moved from using the ComSun namespace to the JDK.star namespace for JDK-specific APIs. So when I say JDK-specific APIs, they're APIs that are available when you're using the JDK, but they're not guaranteed to be available on all other implementations of the Java platform. We then have the unsupported APIs, and these have historically, going back 20 years, been in the sun.star namespace. This has always been, I think, well understood by developers. Sun.star is internal, I shouldn't be using those. Java.star, that's part of the documented supported API, I should use those. But those in the middle, which is the ComSun, have always been a little bit confusing. This is a capture of the website. Mark dug this up, I guess, about a year ago. It's from the JDK 1.0 or 1.1 docs. And if I were to read it out, it's actually what's highlighted on the in the red oval is the sun.star packages are not part of the supported public Java interface. A Java program that directly calls any API in sun.star package is not guaranteed to work on all Java compatible platforms. In fact, such a program is not guaranteed to work even in future versions of the same platform. This is a 20-year-old piece of documentation. So for 20 years, there's always been warning not to use sun.star APIs. But of course, they're ignored. Since JDK 6, the Java C compiler has been emitting warnings if you attempt to use any of the sun.star or internal APIs. So I'm actually curious, has anyone ever seen these warnings emitted by the compiler? One person has, 2 people, 3, 4, okay, a few people have. Maybe I should ask how many people admit to ignoring compiler warnings. Same hands go up. Okay, so just a couple of more slides. Just one is on general compatibility policies, and this is the sort of general compatibility policies for the JDK. If an application is only using supported APIs on release N, then it should work on the next release, even if it's not recompiled. And this has been part of the compatibility story for the Java platform for a long time, most of the 20 years. It's why many developers and many companies actually stick with Java, because they have confidence that their application will continue to work, maybe even faster, maybe even more efficient on the next version of Java. Supported APIs can be removed, but only with additional notice. We've rarely ever done this, but there is a process being put in place for a number of years. I think Mark's, when he was leading Java C6, established a policy for removing supported features, but it's hardly ever being used. There are sometimes incompatible changes to supported APIs, but they're normally very confined to major releases, and they're well documented and strongly justified when it happens. So they're the compatibility policies. There are incompatibilities that come up periodically, and this is how they actually get managed. So at a high level, everyone working on the JDK needs to judge the risk and the impact, and based on actual data. And when we talk about actual data, we will regularly do analysis, both on the source or binary artifacts of thousands and tens of thousands of libraries to get some idea of the usage of APIs and get some idea of what the impact would be when something gets changed. Communicating early and vigorously. So what we're talking about in JDK 9 today and some of the incompatibilities, we have been talking about these for 5 years. There has been many mails on the OpenJDK mailing lists, many presentations, a lot of communication about the changes that we're talking about today. Make it easy to understand how existing code will be affected. So one way to understand whether existing code is impacted or not is to try out the early access builds. So early access builds have been there for many years. Every single week there is a JDK 9 download, which is that week's promoted build, and that allows people to try out the builds and see whether existing code actually works or whether there's issues. We will periodically revise changes based on feedback. So sometimes some feature or some change goes in and it causes problems. People point it out. There's enough evidence to show that change wasn't a good idea, that it breaks existing code. And sometimes that change will either be reverted or change further in order to avoid breaking existing code. Where possible, we'll always fail fast with good error messages, and we will provide tools where possible when there's migration required, and I'll be talking about one of those such tools today. So when removing unsupported APIs, we've tried to provide replacements where it makes sense. There's quite a lot of new APIs that have gone in and been proposed for Java C9 that are standard APIs for things that people would have historically used an internal API for. And provide workarounds where possible. In fact, one of the things that's not very well known about the JDKs is that there are a whole slew of different configuration properties to be able to restore old behavior and keep existing code actually working. All these properties tend to get documented in very detailed release notes that are written for every single major release. But I don't think they're read too often, especially when you start looking at Stack Overflow and you see questions and you realize, oh, that's actually documented in the release notes for 8. That's documented in the release notes for 7. Sometimes they're hard to find. Now we're getting into what I want to talk about in this presentation. And these are, at a high level, the main 6 incompatible changes that there are in 9. The first one is motivated by modules. It's about encapsulating the most of the JDK internals. I want to talk a little bit about changing the binary structure of the JDK. I have a couple of slides on that. That's very important for those that are working on tools that are used to the long-standing binary structure of the JDK. There's a small number of supported APIs are being removed. Shock horror, after all these years, we're removing a tiny number of deprecated methods. Little used methods too. There's some other features that people may not recognize, like the indoor standards override mechanism and the extension mechanism. A change that people may not be aware of is that we've moved to clearly organize, to separate the Java SE from the EE modules, and I'll talk about what that means. And I also want to talk about the version string change. A fairly benign change, you might think, in JDK 9 to move from 8 to 9, or 1.8 to 9 as it happens, but it is a very disruptive change. So I'm going to start with the internal APIs, and I'm going to start with a little graph here, which is based on a data set of about 100 different libraries. And for the most of these libraries that are using the data set here are open source libraries. We use a couple of Oracle products as well, only because they're easy for us to get a hold of and analyze. So the way to look at this graph is that it's a plot of the usages of internal APIs in this set of 100 libraries. The way to read this is that there's 125 usages of some particular internal API. So on the y-axis we have the usage count of specific internal APIs. So what we can see is there's a small number of internal APIs that are used very frequently. Then we have a long tail of other internal APIs that are used very infrequently, only by one or two libraries. So we plot the internal class on the x-axis. So I'm curious if anyone would like to try and guess what the most popular sun.star API that's used by this particular data set that you haven't seen. Sunmisk unsafe, I hear someone saying. Well, that's actually a really, really good guess. But it's not the right answer for this data set. It turns out that Sunmisk unsafe is the second most popular internal API used by this particular data set. The most popular one turns out to be Sunmisk base64 encoder. If I were to put labels on some of the other points on this graph, number 3 would have been Sunmisk base64 decoder. So Sunmisk unsafe is a really good answer. It just happens on this particular data set, there's more usages of base64 encoder. One thing to say about base64 encoder is that we finally, in Java C8, got around to putting a standard base64 encoder-decoder API into the platform. So if you are using Sunmisk base64 encoder-decoder, then have a look at Java util base64 in Java C8 or 9. To see what the real replacement is. I don't know why it took us so long to get around to doing that. So based on analysis like these data sets, what becomes very clear is that the internal APIs can essentially be split into two buckets. Those that are non-critical, in other words, there's no evidence of usages outside of the JDK, or they're only used for convenience. The base64 encoder-decoder is a good example of that. And then there's the critical APIs. So this is the Sunmisk unsafe and a small number of other critical APIs. It would not be possible to implement them outside of the JDK. So these are the critical APIs. And this leads us to JEP 260. This JEP stands for JDK Enhancement Proposal within the Open JDK project, which is where the JDK is developed. All the proposal for features and significant changes have a JEP associated with them. So at a high level, what this JEP, and they're all numbered, proposes is that all of the non-critical internal APIs will be encapsulated by default. When I say encapsulated, it means that code outside of the JDK will not be able to access them. And when I say, remember, non-critical is going to be those where there's no evidence of usage outside of the JDK, or they're just used for convenience. Encapsulate all the critical internal APIs for which supported replacements exist in 8. So where we have introduced standard APIs in 7 and 8, there is no point keeping keeping the internal version available, because code can actually migrate to use the standard APIs. So that's what's encapsulated, all these non-critical internal and the critical internal that have supported replacements. But we will not, the proposal is not to encapsulate the critical internal APIs. So this is SunMISC on Safe, which is used by a lot of very important and high-performance libraries that will continue to be accessible in 9. Going forward then, as there's new APIs and supported APIs are introduced, we can start deprecating and eventually removing some of these critical internal APIs. Now there will be cases where we won't get this right, where there will work, older versions of libraries will want to run and make use of internal APIs in 9 and forward. There'll be a command line flag to allow that code to continue to work, and I'll show examples of that as I go through the slides here. So just the list of the critical internal APIs that are currently listed down in JEP 260. SunMISC on Safe is up there, and for those that are interested in serialization, you've got SunReflect Reflection Factory in there. Those that are interested in logging, things Log4j and others will use SunReflect Reflection Factory, get caller class. There is actually a stack walking API in Java C9 that came in with JET 259, but there's still a lot of existing code using get caller class, so that's identified and as remaining around in 9. There's also some support for signal handling because there isn't a standard API yet in the platform for signal handling. There's been a couple of attempts at introducing standard APIs for this, but there's nothing that really stuck. So there's nothing in 9 at this time for a standard way to do signal handling. So this list of internal APIs continues to be accessible to applications in 9. Now I'm going to go back to the 100 or so products that I had on that were plotted a few minutes ago, and we list down what was in this data set. So remember we had 125 usages of SunMISC Base64 encoder. We knew that Unsafe was the second one used. This is the full list of internal APIs, or at least most of them that were used in that slide. So just the color codings here. Orange is a critical internal API. That is why SunMISC on Safe is orange. That's why SunReflect Factory is orange. Purple is the non-critical APIs that have supported APIs. So if you look at, for example, there's a whole bunch of Sun image codec APIs in there. There is a standard image IO API available since I guess 1.4. Green is not critical, not supported in 9. So you'll see a number but supported in 9. So you'll see, for example, org W3C DOM XPath. This has historically not been a supported API in the Java C platform. It was realized this is actually being used. It should be a supported API. So it was moved in JDK 9. And red then is those that don't have any replacements. Sorry, these are will be encapsulated, and someone will need to use a command line flag or some way to actually break into those APIs if they continue to use them. Now let me talk a little bit about finding API usages of internal APIs. Do you mind if I just quickly ask who is aware of the JDEPS tool in JDK 8? Okay, maybe 5 or 6 hands went up there. So when I talked about preparing for JDK 9 and I talk about at least providing some tooling to help identify issues, JDEPS is one of the useful tools that went into JDK 8 that allows you to do static analysis on existing libraries or a class path of jar files and identify what their dependencies are. One of the most useful options with JDEPS is the JDK internals option, which will quickly tell you whether there's any static references to JDK internal APIs in any of those jar files. So very, very useful. For those don't have Maven projects, there is an equivalent Maven plugin that uses JDEPS And you can integrate this into your projects to be able to identify JDK internal API usages, and it can be configured in multiple ways. So you can actually have the build fail if you use an internal API, or you can have the build at least flag in its log files what internal APIs are being used. So that's integrated with JDEPs, which is quite useful when you're on 8, you're thinking about 9, do I have any code that's using internal APIs? So here is an example output. This is running on one of the Glassfish jar files. So the command I'm using here is jdeps-jdk internals and then the name of the jar file. And I'm getting some output here. So this is a security jar file that comes with the Glassfish app server. What we see in this output here is a whole bunch of usages of sun.security.something APIs. I think what has happened here is that someone working on Glassfish at one point started using the internal framework for security providers within the JDK. So that's why there's a whole bunch of usages of sun.security classes. The important thing is it's an easy jar file to be able to run this on and see what internal API usages are. The other thing about this output, in addition to it telling you which sun.star APIs are being used, is there's a little table built into this. It has that will point to standard APIs that could be used as alternatives to some of these internal APIs. So right down the bottom, if you can read it, there's code in this security jar file that's using Sun Security X500 name. But there is a standard API, JavaX Security Auth X500 principal, that has been in the platform since 1.4, and that might be a viable alternative to use if this code is being updated. So that's JDEPs. If you only remember one thing from this presentation is JDEPs is a really useful tool to run your own code to get an idea of what internal APIs might be used. So continuing with the example of Glassfish, I want to show you what will happen if you were to run this code. So I'm not recompiling it. I'm just going to take Glassfish and run it on 9 and see what actually happens if I were to run this code. I get a scary exception. This scary exception is an illegal access error. If I were to read it out, it says class ComSun enterprise security provider policy wrapper. So this is a class that's in the Glassfish security jar file. Cannot access class Sun security provider policy file. Ignore the rest of it because Java base does not export Sun security provider to unnamed module. And then I get a stack trace. What's happening here is the VM is throwing an illegal access error because there's code in this Glassfish jar file attempting to link to an internal API, and it is failing at runtime with an illegal access error. So it's a scary exception. Now, if I were to attempt to recompile this code with 9, I would get a compilation error. So the reason is that when we get in looking at modules later on in the afternoon, module boundaries are supported at compile time as well by the compiler. In this example, I'm just taking a pre-existing, pre-compiled Glassfish and I'm trying to run it on 9 and I'm getting a scary error. I'm going to take another example, another G example. This one I've just taken an old version of Gradle 2.7, so it's a couple of old versions, and I'm attempting to compile some Java code with it, and I get an error. I've highlighted it in red. Could not create an instance of type ComSun tools JavaC API JavaC tool. This is not a very helpful message, but for those that are used to Gradle, you know that you can actually run Gradle with the -- stack trace option, and it gives a more useful stack trace when it gets an exception. And the exception I get here is another scary exception. This one is an illegal access exception. So the previous one with the Glassfish example was an illegal access error. This is what we're getting with the exception is the core reflection equivalent of an illegal access error, which is an illegal access exception. And if I were to read this one out, then what I have is org Gradle internal reflect direct instantiator cannot access class ComSun tools JavaC API JavaC tool. So what's happening here is that something in this version of Gradle is attempting to use reflection to access some internal type within the Java-C compiler. And it's getting exception because the module system says, no, that's not exported. You can't access that. No, don't worry too much about Gradle. It's moved on a couple of versions since then. This code has changed. But I just wanted to get across the point that when we're talking about encapsulating internal APIs, it's not just for static references. It's not just for at compile time. It covers everything, including reflection and method handles and so on. Now, this is a huge change. So retrofitting modules to the platform after 20 years and having strongly encapsulating internal APIs is a huge change. We don't want to break existing code, but we know some code will actually break. So there is always a get out of jail card. And in this case, it's a command line option, which is called add exports. So for the Glassfish example, we saw that it was using a whole bunch of different internal types in the Sun security package. So the way we can get this existing code to run is by running Glassfish with a bunch of additional add export options. I'll explain the add export syntax in a few minutes, but just take it that I'm essentially I'm taking responsibility when I'm running Glassfish to that I want to break encapsulation to allow Glassfish get at the Sun.security packages in the JDK. So that's the command line option. In addition, I didn't mean you don't wish to pick on the Glassfish. This is actually an issue that's actually tracked in their JIRA, and I'm sure will be addressed at some point in the future. Now let's look at the command line in a bit more detail. There's three parts to the value to this option. There's a source module, the package, and the target module that you want to export it to. We'll be talking more this afternoon about the different modules in the JDK, and one of the things you'll see on many, many slides is the core module of the platform is called Java Base. That is where Java Lang object lives. That's where the core APIs are. That's where the Sun security provider package is that Glassfish is making use of here. So when I construct the add exports, I'm telling the system what module, what package in that module, and who are you exporting it to? Who are you making it available to? And there's a special token called all unnamed, and you'll see a bit more about as we work through the slides today what this means. Just for now, just think of it as the class path. In addition to the command line option, we have a way to do this with executable jar files as well. So you can do the equivalent of the command line in the main as an attribute in the manifest of an executable jar file. So if I were to run Glassfish as in java-jar glassfish.jar, I could get the equivalent of that command line option by adding an attribute just to the application jar file to indicate what internal packages that this application needs to break into. And that's there solely just to keep existing applications working. You would hope in time that the internal API usages would be removed and migrated. So that is the main implication of encapsulating internal APIs on existing code. They may fail at runtime, they may fail at compile time, but there are command line options both at compile time and runtime that allows existing code to continue to work. The next thing I want to talk about is the structure of the JRE and the JDK. So I want to talk a little bit about the motivations because this is not really an API change. So moving to modules. Oh, Mark just is asking if there's questions, bring them up as we go along. It's we've a long session today and it's informal. So if there's any questions as we go through this, then just raise your hand and we'll try and answer them. So moving to modules it completely blurs the historical distinction that we've had between the JRE and the JDK. The JRE we know as a runtime image that is there for running applications. It doesn't have the tools, it doesn't have the compiler, and so on. The JDK is the runtime plus a bunch of tools. As you'll see today as we go through some of the examples, this completely blurs because we can create runtime images that have different subsets of the platform. So that's one of the motivations for changing the binary structure. Second motivation is the JDK has always stored its classes in jar files and are way, way back zip files. But since JDK 1.2, all of the classes for the core platform have been in a jar file called rt.jar. Most people, I will guess, have heard of rt.jar. Jar files are based on the zip format. The zip format is really, really historic at this point. We can do things much more efficiently if we move from the zip format to something that's more high performance, that doesn't have all of the attributes that zip files have. So this is another motivation for changing the binary structure of the JDK. We can do things a lot more efficient than zip, which is designed, 30 odd years ago. So this change to the binary structure, and I'll show a few slides as we go through this, this is very disruptive to tools and libraries that are used to poking into the JDK, locating rt.jar, enumerating classes, and so on. If there's no jar file for them to find, then they have problems. So this is why we put this into JDK 9 back in 2014. We wanted to give a lot of time to the IDEs and the other tools that are used to accessing directly files in the JDK. The other part to the binary structure is that for the first time we have introduced a supported API for these tools to access classes and resources in the image. So instead of having to use the jar API and go and find rt.jar, we now have a supported API for tools that are running on 8 or 9 to be able to access a JDK 9 image. So here is a JDK 8 image, a runtime image. This has been mostly the same as it has been since 1.2. There are two levels in this. There's a top level JRE directory, which is where the runtime lives, and when you look at this closer, you'll see there are two bin directories. So if you download the JDK 8 or 7 or 6 or 5, there are two bin directories. You'll actually see the same tools in both directories. There are two lib directories for jar files. Right down in the JRE lib is where you find rt.jar and a bunch of other jar files. The top level lib directory is where you find tools.jar and a couple of other tool-related jar files. This is the historical format. There's a lot of opportunities to clean up this as part of moving to modules. And this is the modular runtime image structure that we've had in JDK 9 for the last 2 years. It's a disruptive change, switching from that previous slide to this slide. But important things when you look at this new layout is it's very, very simple. There's a bin directory where the tools are, as before. That's where you find Java. That's where you find Java-C. That's where you find RMI registry and all the other tools that you're used to seeing in the bin directory. There's a conf directory, which is a new directory where all of the user-editable configuration has been moved in there. When you look at JDK 8, 7, and older, there's a lib directory. Well, there's two lib directories. There are properties files, there are security policy files, there's other configuration files. It's always been confusing as to what can be edited, what makes sense to edit, what will break the system if I change it. What we have done is use the opportunity to do a clean separation of all of the configuration. So anything that can be configured is moved into the conf directory. That's where you'll find the security file. That's where you'll find the properties file to configure the management agent, and so on. The lib directory is now just a directory where the JDK will put files, but it's not intended to be used by anything directly. rt.jar is gone. In fact, there are no jar files in the JDK now. Everything has been moved to a new, we call it a JImage format, which is something that is designed for very efficient class loading, efficient space, and we've got a whole bunch of optimizations that we can do with tools like JLink that you'll see later on today. So this format is not documented, and it's deliberately not documented because we want those working on the JDK need the flexibility to be able to change this at any time. So that is the simple structure of the new runtime layout. Any questions on that? Okay. Right. Shock horror, we're removing 6 deprecated methods. So we've been looking at modularizing the platform for a long time. And what was identified quite a long time ago was these 6 methods in Java util logging, log manager, and Java util jar pack 200, packer and unpacker, are an impediment to moving to modules. We can't have a clean separation between the core module and the desktop module without removing these methods. So these are deprecated methods. So something like log manager, it allows you to add or remove a property change listener. There are alternatives to that are in 9. So removing these is actually turns out not to be a big deal. These have been removed since JDK build 1, which is January 2014. To my knowledge, there hasn't been any bug reports by anyone. So we're confident that these are not frequently used. In fact, when we run static analysis of tens of thousands of artifacts in Maven, we see very few, if any, usages of these. These have also been flagged for removal for a long time. So there was an update to the Java C8 JSR, which actually marked these as for removal. There's some mechanisms here that you may not have heard of: the endorsed standards override mechanism and the extension mechanism. At least one or both of these were misfeatures. Primarily used by app servers, and these have been removed in 9. The reason they have been removed is because everything has moved to modules. The idea of being able to override things via these mechanisms just doesn't make sense now. We have much better ways of actually overriding things in the JDK with what we call upgradable modules, and we might see a little bit of that later today. So that's a couple of things removed. Now I want to bring up something that initially might look a little bit esoteric, but let's work through it. Let's consider this command: java-cp jsr305.jar something something. For those that are used to static checkers, then you'll recognize our defect detection. You'll recognize JSR305 as the jar file that has the JavaX annotation not null, nullable, all of these other things for doing static analysis and defect detection. It turns out these are in the same package as the JSR250 so-called common annotations. That's where and the common annotations are something that are, well, at least a subset of them are part of Java C. So when you look at a command like this, you realize we have actually a split package issue, and you'll hear the term split package as we go through some of the module slides today. We've got JavaX annotation not null being loaded from the class path, and then you've got the JSR250 types in JavaX annotation also being loaded, but they're loaded from the module that's in the JDK. So this is a little bit of a mess. And this is just one example. We have another couple of these ones with the transaction API. Java C defines a subset of the transaction API. So if you put the rest of the EE version of the transaction API on the class path, you end up with similar kind of split package issues, slightly worse. Things go completely over the cliff when you start deploying your own versions of Corb on the class path. And it's amazing that these things have actually worked. So we've been looking at this problem for quite some time, and it really just comes to light with modules. And the proposal at this particular point for JDK 9 is that these Corba and the modules that are effectively owned by Java EE will not be resolved by default. There's 6 modules involved. By the way, when I say modules, we'll talk about the platform modules in a minute, but they all start with java.something. The Corba module is java.corba. The Java transaction API is java.transaction, and so on. There are 6 of these that are problematic in the JDK. Most of these 6 have actually got lead a double life. They are standalone technologies in the JCP. They rev at a different pace to the JDK. They've always been technologies that app servers have historically upgraded or replaced because they were never happy with the version that JDK shipped. So the proposal is that these not be resolved by default. Not being resolved by default means that the types in these modules will not be visible. You'll effectively get a no class def found if you attempt to reference any of the types in these modules, because they will not be resolved and none of their types will be visible. So this proposal has a couple of motivations, but one is to avoid the unnecessary conflicts with popular libraries like the JSR 305 that I showed in the previous slide. And the second motivation is really just to make it easier for existing app servers to migrate to JDK 9. They're used to upgrading a lot of these components already, and that will actually work a lot cleaner if these modules are not resolved. But this is a policy that we will have to examine as JDK 9 goes on. So more people trying out the JDK 9 builds and seeing whether they have issues, whether they have dependencies on any of these APIs, and whether using command line options to work around these issues are going to be problematic or not. So for this particular example, then there's a number of different ways you can work around it. You can use the add modules option. So as we go through the slides today, you'll see there's a whole bunch of new command line options related to modules from the Java launcher. In this example, I can use the add modules Java Corba, and what that will do, it'll add the java.corba module as a root module to resolve at startup, and things will just work as they did previously. I can deploy an alternative implementation of the Java Corba module. I talked earlier or briefly just about the indoor standards override mechanism going away. That was the way the app servers upgraded components. That's the way the app servers would have upgraded, and with new versions of the OMG and Corba APIs. They can do this via modules now, but they can deploy a new version of the Java Corba module on the upgrade module path. The upgrade module path, just as a high level, overrides the version of the module that's in the runtime image. Or if I don't care about modules, then I can just put my Corba jar file on the class path and it'll just work. There's no split package issue, there's no conflict with what's in the JDK because the Java Corba module is not resolved by default. Very, very simple. All the details around this, by the way, are in JEP 261, and that's where you'll see documentation, all of the command line options that I will go through today. Okay, a couple of other changes. The first one turns out to be quite a disruptive change. Historically, the application and the extension class loader were instances of JavaNet URL class loader. That is no longer the case. It's now a completely different implementation. Because we've moved to modules, we've completely changed the implementations of these class loaders. We've never documented what the implementation type is of these class loaders, but it turns out there's actually a code out there that has made assumptions, and they will call class loader get system class loader, cast it to URL class loader, and then maybe use set accessible to hack into the protected add URL method. We've seen this a couple of times. So this is an important change to get over, because now what will happen is if the system class loader is no longer an instance of this, you attempt to do a cast, you'll get a class cast exception. Moving to modules means that the boot class path as we know it is essentially gone. The boot class loader remains, but the boot class path is essentially gone. It stays around for a particular case with agents, but not interesting here. For the most part, assume that it's gone. That means the command line options that we used to configure it, to either override it or to add to it or even prepend to it, those options are gone. We've known about this for quite some time, and there's options in JDK to be able to catch these usages if you want them flagged. Similarly for the extension mechanism. The system properties related to the boot class path, of course, are gone as well. There's no boot class path, there's no system properties. All the details around this are in the JEP 261 that I mentioned earlier on. So if you want homework reading on all of the changes related to this type of detail, it's all in JEP 261. Now I'm going to move on to something that is not motivated by modules, but is a disruptive change in JDK 9. And this is all documented in JEP 223. Our Project Verona is where the implementation of this is done in JDK. So maybe I'll just wake people up with a quick poll and ask whether people think the JDK versioning scheme has been confusing. A couple of people, okay. Well, let me just provide one of the motivations for reading out a paragraph from the JEP. Which release contains all of the most recent security updates? Is it JDK 7 update 55 or JDK 7 update 60? It looks like JDK 7 update 60 is 5 releases later than update 55, so therefore it must include more security fixes. That conclusion is incorrect. These two releases both contain exactly the same security fixes. Security releases based on the previous minor release are odd numbers incremented by 5 or by 6 if necessary in order to keep the update number odd. It's very, very confusing. So what's happening is after all these years is the version scheme is being re-examined and changing, and this will impact the output of java.version. It'll impact the system properties that report the version, and I'll show some of these in the next couple of slides. So here's the old and the new. I have only one thing to say about this slide. After 20 years, the leading one is gone. And here's the system properties, the old and the new, from before the transition to the transition. These version changes have been in JDK 9 for close to a year. It was just at the end of 2015 when these changes were pushed in. It turns out to be quite a disruptive change. There's a lot of code out there that looks at the value of the java.version property and parses it on the assumption that there's a leading one dot. So this is a disruptive change to get over this. There is a new API for versions. If you have a look in the Java doc for Java C9, you will see there's a Java lang runtime version method that will return you back the version. You can query that version in for its major number. It's much simpler to work with versions in 9. So I've talked about disruptive changes for most of the last half an hour. I just want to talk now about a couple of JDK 9 features that help with the migration. And these are both JEPs. JEP 238, which is multi-release jar files, and JEP 247, which is compiled for older platform versions. So let's start with some motivation. So assume my application is making use of internal APIs, or some library I'm using is making use of internal APIs. This is not going to work on JDK 9 without a command line option. However, when I look at 9, I see there's a whole bunch of new APIs for things. And what I would like to do is start making use of those APIs. So it might be I'm moving from something to var handles, or I'm moving from some org Apache, common internal org Apache, blah, 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 serializer to the new catalog API. So I want to move code from using internal APIs to using new standard APIs. But I have a constraint that I want to be able to continue to be able to compile to JDK 8 because the users of my library, many of them are going to be on JDK 8 for a long time. And this is where multi-release jars come in. With a multi-release jar, what has happened is that the jar format has been extended to allow multiple Java release-specific version class files to coexist in the same jar file. To explain this, let's look at an example here. What I've got here is assume my application is com, acme, stats, CLI, stats, and I've got a bunch of packages in there. I'll assume that I've got helper code that's making use of internal APIs. But I've also got a version 9 of this helper. I've got a version of my helper class that uses only standard APIs that I want to work on 9 and newer. So what I can do is I can construct this thing called a multi-release jar file. And I put the versions of the classes that are for 9 and newer, I put them in meta-inf versions /9, and then the same path to the resource or to the class file. In addition, in the main manifest of this jar file, I will add a new attribute called multi-release, and I'll give it a value true. So what happens then is I've ended up with a jar file that has two versions of helper.class. One version that's suited for 8, or maybe I've compiled it for something older, and I've got a version for 9 and newer. And now let's run this and see what happens. When I do run I assume it's an executable jar as well, and we'll do java-jar. When I run this on 8, then the version of com-acme stats internal helper will be loaded from the top level section of the jar file. So assume this is compiled for 8 or older. When I run it on 8 on the class path, this version of the class file will be loaded. When I run it on 9, then it will pick up the new version, it'll pick up the 9 version from the meta inf versions 9 section of the jar file. So this is really, really useful because it provides a way for you to release a library that'll work as it always did on 8 and older, but makes use of new APIs that are in 9 when it's running on 9 or newer. So this is quite useful. Now, when you start thinking about this, you immediately start to be concerned about, oh, does this mean I need 2 versions of the JDK in my build environment in order to produce one of these things? Well, it turns out you don't have to do that, and that's because this is what this other JEP is about, this compiling to older versions of the platform. So historically, when you wanted to build something for an older version of the platform, then you had to you specify the source version and the xboot class path to Java-C. In order for that compilation to work, then you needed to have the JDK for that older version somewhere on your system, because you're specifying the location of that to xboot class path. Now, with 9, it's much simplified. There's a new option, -- release, and you give it the major version of the platform that you're targeting. And this, so you can do java -release, sorry, -- release 6, or -- release 7, or -- release 8, and it will compile those classes for that version of the platform. You only need a version 1 JDK 9 on your system. You don't need the older version in order to do this compilation. Now, in time, we will see, and I think Robert Schulte talked a little bit about this yesterday, is there will be Maven support for this, which will make it a lot simpler, I think. Okay, so this is mostly about, we're done on this deck, and we'll move on to modules now in a few minutes. So just a few points when you start thinking about JDK 9, and most people here didn't raise their hands to say they were trying out JDK 9. If you want to take one thing from this presentation, is write down JDEPs and try it on your existing code. It's a very, very useful way to do static analysis of your application and your libraries to get an idea whether they're using internal APIs or not. Encapsulating internal APIs is by far the most disruptive change that we've ever done in the JDK. So it's important that you have some idea whether this is going to cause you problems or not. As we've seen, the change to the version string and dropping the leading one turns out to be quite a disruptive change. We've seen a lot of libraries over the last year that have had problems because they weren't parsing the value of java-version correctly. So if you've got code that's doing that, check it out to see whether you have any problems. Mostly for tools, but if you have code that is used to going directly into the JDK's lib directory, finding rt.jar, other jar files, and accessing the classes and resources directly, then now is a good time to look at that. Have a look at JEP 220, have a look at the file system API, which provides a supported way to access the classes and resources in a runtime image. And the other thing then, of course, is try out the JDK 9 builds, or if you're really, really brave, the Jigsaw early access builds, because everything is, there's builds go out like clockwork every week, and it's a great way to actually to test whether your existing code works or not. If you're feeling really brave again, try out some of the new features in 9, particularly the multi-release jars, which provides a really, really good way to be able to have code that targets 9 and newer, but still you're releasing a library that works on 7 or 8. And that's it for this deck. So more information on what I've talked about here is Project Jigsaw page. We'll bring this one up again later on when we talk about the module system. the location of the JDK 9 early access builds, which is jdk9.java.net/download. The JDEPS tool, which I talked about, has its own wiki page, and that wiki page includes some sample commands, and it also includes a table of internal APIs versus some standard APIs that would be better, should be used instead. And then the links to the JEPs that I mentioned today, the version string change and the multi-release jar. Okay, so that's it for these slides. Does anyone have any questions before we move on and start talking about modules? A question. Okay, so I think that if I heard you correctly, is with a multi-release jar, you're asking if the JDK has support for all the older APIs? Is that what you said? Right. Okay. So okay. So if okay, so I think the question is whether the JDK has the APIs for all the older versions. Okay, so the first thing is for the standard APIs have always been added. It's always been incrementally adding to it. So nothing has been removed. So if you're only sticking to standard APIs, then code that's compiled against the 6 API should run on 7, 8, and 9. It's only in very small exceptions that things have been removed, as I listed out here today. Internal APIs is a little bit different. The internal APIs, there's always going to be churn in every single major release, and we've had more churn on internal APIs between 8 and 9 than has ever happened. Now, with the multi-release jar, what you will have is let's suppose it's 8 and 9, or even 7 and 7. Let's suppose okay, we'll stick with 7 because you mentioned that, I think, is so you will compile the code that's using the internal APIs for 7. And then you will have an alternative version, which will be used on 9 and newer, that will use the standard APIs. You construct the jar file like I showed in the on the slide. So when you're on when you are on 7 or 8, it'll load the versions from the top level section and the others. Yeah. So your question then, I think, leads then to what if those internal APIs aren't on 9 when you're compiling it with 9, in which case it won't compile. You would have to use the more verbose version, which was Java C-source 7-target 7, and then you would have to provide the JDK where that internal API exists. Yes. So hopefully that's kind of answered your question. Any other questions? Quiet today.
Okay.
I will just bring up the intro slides. This is a fairly short deck. And I guess do we take a break in the middle of this?
Yeah. We don't have to, but we should.
Okay, intro to modular development. So this is number 2 talk. One background slide this time. And this is just to give you an idea of more numbers. So the Java Platform Module System is being developed in the JCP, or Java Community Process, via JSR 376. This is what the module system, Mark Reinhold, is leading this JSR. Java C9 has its own JSR in the JCP, which is number 379. And that will own the modularization of the Java SE APIs. You'll see some of that as I go through the slides here. They're all specs and standards. Within OpenJDK, where we do the implementation, we have a whole bunch of JEPs, and this is where we're producing the reference implementation of Java C9. For the module system, we have 200, 201, 220, 260, 261, and 282. This all sounds like gobbledygook, but this is where we actually document the module graph. It's document how we organize the source code of the JDK as modules. It's where we document the binary structure that I showed in the previous presentation, and all the issues around that. It documents what internal APIs will be encapsulated. I mentioned 260 in the last presentation. 261 is a huge big JEP where it documents all of the details related to the module system, all implementation, and related to class loaders, command line options, and so on. All the details are in that. And 282 is the linker, or the JLink tool. You'll see a little bit about that today. Now we'll move on in intro to modules. Part 1, which is modular development, starts with a modular platform. I don't know what to say with this slide. This is actually a slide of a graph as to where we were with the JDK in JDK 7. It looks kind of messy. So what we were faced with is turning this graph into a set of cohesive modules. And a lot of progress has been made since then. The one thing I will point out in this messy slide is near the top in red is base. That name has stuck. And you'll see base, or actually java.base, as we work through the presentations today. So we move from this messy slide to this graph. This is what JDK 9 looks like now. And this is just the standard modules. Standard modules are the java.star modules. There are a bunch of other JDK-specific modules that start with JDK.something. We might see a few of those today. So this looks a lot cleaner. A couple of points to make about this slide is, for the most part, there is only one technology per module. When you look at this graph of modules, it's extremely hierarchical. And this is mostly a consequence of headful versus headless, splitting the core from the desktop area in particular. Another important point about this graph is there are no cycles. And you'll hear a lot more about cycles in Mark's talk later on today. The Java base module is right down the bottom of this slide. And if you look closely, and some of the edges have been removed just to simplify this, there is a directed edge from every module to Java base. Java base is the core of the system. I said earlier on about it, that Java base is where Java-lang object is. Everything depends on java.base. Now, what does it mean to be on a modular JDK? Does it mean my existing code that I run today is going to have a problem because I'm using the class path? So let's explore this a little bit. So I'm taking here a Java-version of a recent JDK 9 early access build. This is build 142. It's actually not last week, it's actually the week before, because last week was 143. Java version prints out similar format to what it always does, except it's the new format rather than the old format. Now I'm going to run something with this JDK 9 build. Now, for this slide, I've just randomly picked the JEditor text editor. It's just a text editor written in Java. It's been going a long time. It ships as an executable jar. I have no idea whether the maintainers of JEdit have ever tried JEdit on JDK 9. What I wanted to try is just to see how it would run, and it works exactly the same way as it does in JDK 8. The point is that I can take an existing code, run it as an executable jar, or use the class path exactly as before, and as long as code is using standard APIs or supported APIs, as per the previous presentation, that code should run in exactly the same way as it did previously. Now I'm going to bring back my module graph, and I'm going to, on the left side here, is show the output of Java -list-modules. So what I've been running here is something on the class path with Java-jar. but my actual runtime, or the platform, is composed of a set of modules. And what the list modules option to the Java launcher does is it lists down all of the modules that are part of the system runtime. And I've stripped this down a bit just because it wouldn't all fit on the slide. But you will see here that it lists down the names of the modules that correspond to all of the nodes in the graph that I showed a few minutes ago. Now we'll explore one or two of these modules to get a feel for what modules you're actually running on when you're using a class path with 9. So here is the output of Java --list -modules Java base. So Java base is the core module. So what we see here is a bunch of exports. And these are all of the core packages in the platform. Java IO, Java Lang, Java Lang Invoke, Java Lang Reflect, and so on. These are all the core APIs, and these are exported by the Java base module. Applications and other modules can make use of the APIs that are in these packages. In the Java base module, you will not find any non-core APIs. There's no JDBC here. There's no SQL here. None of those are in the base module. You won't find Swing or AWT here. Instead, you'll find those modules in the desktop module. So I'm repeating the list modules command, but I'm asking you to list out and describe the Java desktop module. The Java desktop module is the module that exports AWT and Swing. So as per the previous slide, there's a whole bunch of exports, and they're all at the granularity of package. So the Java desktop module exports Java AWT, Java AWT color, Java AWT font, and so on. You'll see Java X Swing in there. All of the desktop APIs are grouped into this module and exported by this module. In addition to the exports that you see here, at the bottom of the slide, you'll see its list of dependencies. You did not see any dependencies when I list out the Java base module. The reason is the Java base module does not depend on any other module. The Java desktop module, however, depends on 4 modules: the Java prefs module, Java transfer module, Java XML module, and the Java base module. Ignore the detail that is transitive and mandated here. We'll get into some of these details as we go through the slides. The important thing is that every module that's in the platform has a clearly declared set of exports and a clearly declared set of dependencies. And one other thing I want to introduce in this first section is the JLink tool, or the linker. This is JEP 282. Because the system is now composed of a set of modules, it means that I can start creating runtime images that only contain a subset of the modules. So when I look at my JDK today, I will see that there's about 65 or so modules. In addition to the Java.star modules, there's another JDK modules for tools and so on, and service providers. I can use a linker tool to link a small subset of these modules and create a runtime image that only contains those modules. Remember from the previous slide, a runtime image is this modular runtime image structure now, which is very, very simple: flat structure, bin directory with the tools, conf directory with configuration, and then there's other directories that are just not documented. What I can do with the linker tool is I can ask it to produce one of these runtime images, and I'll tell it which modules to include into that runtime image. So here's a sample JLink command. So JLink is the name of the tool. I give it a bunch of options. One is where to find the modules. This is the module path. We'll go through module path in more detail in a few minutes, but just for now, assume this is the directory where to find the modules. I tell it what modules I would like to include. So this is what the add modules option is. And it's going to produce an output runtime image. And so I give it the -- output option to tell it where to produce the runtime image. I run this command, and I'm going to now run the list modules on this generated runtime image, and I'm only seeing a small subset of modules. I'm seeing 1, 2, 3, 5 modules here. So a minute ago I showed the output of list modules Java desktop, and you saw that it depended on 4 other modules. what I've done here is I've asked it to produce a runtime image with Java Desktop. It's going to link in Java Desktop and its transitive dependencies to into this runtime image, and that is why I've ended up with 5 modules. Now I can go and run JEdit again. This time, not with the full JDK, not with the JRE, but with this small runtime image that I've created with JLink. And I just do java-jar jedit.jar, and it just runs exactly as it did on the JDK, but this time with a much smaller image. So JLink and being able to reduce these runtime images, this is going to be a huge step forward for redistribution in the future. So that is the end of part 1. So we've moved from the messy slide, the monolithic JDK, to in mostly a set now of mostly cohesive modules, which is really good. Every one of those modules has a clear set of exports and a clear set of dependencies, which is really good. Even though you're on a modular platform, the class path works exactly as it did for the last 20 years. You can remain on the class path until you retire. It's not going away. The JLink tool, which I showed on the last slide, allows you to create runtime images with a subset of the platform modules. And having a modular platform is a great start for modular development. Okay, I'll move on now and we get back to basics on modules. Any questions before I get into the second part? All right, we're quiet here today. Okay, so we're going to start right at the beginning and ask the question, what is a module? The first thing about a module is it has a name. In the previous slides, you saw some of the platform modules, Java Base, Java Desktop, and so on. I'm now going to be creating my own modules. For this example, I'm going to create a module that is a statistics library, and I'm calling that module Stats Core. That is the name of the module. The contents or the code in a module is organized by package. For this example module, I have types in 2 packages, COM-ACME Stats Core Clustering and COM-ACME Stats Core Regression. All of the types in my module are in these packages. There may be other packages in there. Main point is the code in a module is organized by package. A module may have native code, and a module may have other resources, may have configuration. We'll ignore that for this part of for now. In source code form, the module self-description is expressed in a module declaration, which by convention is in a file named module-info.java. And it sits in the top level directory of the source tree by convention. So for my stats core module, I will have a module declaration. I use the module keyword, module space, module name, open curly brackets, close curly brackets. We will fill this in as we go through the next couple of slides. This is in a source file that sits in the top level directory of my source tree. We will assume for the example I've got a couple of types in there, cluster.java and linear.java. They're my source code. My module declaration can have one or more requires clauses. This is where I declare my dependencies. For this example, we will assume that the stats core module has a dependency on the Guava module. We will assume the Guava module for now. So the dependency is declared with the requires clause, so that's require space module name. As I build up these module declarations, I'll show a little graph on the right. So we'll see this dependency graph build up as we add more to it. So that's our stats core module. I now want to introduce a second module, stats CLI, which will depend on stats core. And let's see what this looks like. So this is our second module. Stats CLI requires stats core, so it has a dependency on my stats library. In addition, it has a dependency on java.sql. Java SQL is the platform module that exports the JDBC API or Java SQL. So I've got a second module now with depends on 2 other modules. As you saw from a few minutes ago, every module depends on Java base because that is where JavaLang object exists. The module declarations I showed on the last couple of slides do not say requires Java base because every module depends on Java base whether you declare it or not. So that is why in this graph there's a directed edge to say that stats CLI depends on base, stats core depends on Java base, Guava depends on Java base, Java SQL depends on, everyone depends on Java base whether you declare it or not. So now I'm going to resolve this and generate the transitive closure, and I end up with a dependency graph like this. So the additional nodes that have suddenly showed up on this slide are the Java XML and the Java logging module because Java SQL depends on them. When a module depends on another module, we say that it reads the other module. So stats CLI depends on Java base, therefore it reads Java base. Stats CLI depends on stats core, therefore stats CLI reads Java core. This is actually going to be important because this readability relationship that we're going to spend a couple of slides on is really the basis for reliable configuration. Now we're going to start looking at a couple more, one or two more concepts. So I'm going to pick out a small subset of the modules to look at here. We'll look at stats CLI requires Java SQL. Java SQL requires logging. And we start putting a little bit of code in here just to see what issues might show up. In the Java SQL module, there is a type driver, Java SQL driver. I guess most people have seen that. The driver class is public and has a public method called getParentLogger that returns a logger type. The logger type is not in the Java SQL module. It's in the Java logging module. That is why Java SQL requires Java logging. As the consumer of the JDBC API in the stats CLI module, I will start making use of the getParentLogger. And I might, for example, use method invocation chaining. I might get my driver, getParentLogger, call the log method. Now what's going to go on here? Does it mean that the stats CLI module needs to require the Java logging module? That's kind of annoying, but it will work. I could actually, as the Java SQL module, I could ask all my consumers, if you're using this module, make sure that you also require the Java logging module. It will work, but will be annoying. So what the module system does for this kind of usage is it has a modifier on requires, which requires transitive. What this does is it means that stats CLI will read the Java logging module. So in the middle we have Java SQL requires transitive Java logging. Anyone that reads Java SQL will also read Java logging. This is not re-exporting of APIs. This is what we call implied readability. If I require and I read Java SQL, I will actually read any modules that it requires transitive on. You'll hear a lot more about this in the under the hood later on. So this orange edge that I've added to the graph here, and you'll see more of them, is the edges that are added because of implied readability. A few minutes ago we had the transitive closure and we had our dependency graph. When I add the edges that are induced by implied readability and that requires transitive, I end up with this readability graph. That's exports and readability. I now want to move on to the next concept and we'll bring everything together to see how accessibility works. So in addition to a module declaring what other modules it depends on or requires, a module also can use export clauses to declare the packages that it exports. So our stats core module is our statistics library that we're using as the example. It exports two packages, ComAcme stats core clustering, ComAcme stats core regression. All the API of this module is in these two packages. We can think of a module as being split into two. One part of the module is where the packages, the exported packages, that's where its API lives. There's then some internal packages possibly, and for this example I've used acme stats core internal, where I've got some internal types that are part of this module. They're not part of my API, they're not intended to be used by anyone outside of my module. They're not exported. Exports, as we work through this, is the basis for encapsulation, as we will see. So now let's bring together our readability and our exports to show you how accessibility works. And here we have it in a simple example. Stats CLI requires stats core, therefore it reads stats core, and it can access any of the public types in stats core's exported packages. It cannot access any of the types in the internal packages. This is a two-way street. Oops, sorry. If stats CLI did not read stats core, then it cannot access any of the types in stats core. If it reads stats core, then it can access any of the public types in stats core's exported packages. So that's why you've got a two-way street. Readability, exports. If you get this concept into your head, everything from modules just flows from that. And the main thing you can deduce from once you understand accessibility is that what we have known as public no longer implies it's accessible. This is a big, big change with modules because I can have public types in my internal packages that are not accessible to anyone outside of my module. In the Under the Hood talk later on this afternoon, Mark will go through all of the much more details on this. So I'm now going to move on and start talking a bit about command line options and how to compile modules, package modules, and run modules. Is there any questions on any of the concepts before we get into any of that? Oh, we have a few questions, Mark. Arise.
If you have an accessible interface, but a not accessible implementation of the interface, how does that work?
Okay, so I think the question is, if I heard you correctly, is you've got an accessible interface. So the interface is public and an exported packages, but an inaccessible implementation because it's in a non-exported package. And how does that work?
How does it work today? What if I have a public interface and a package private implementation class, and I return an instance of that class? Does it work? Yep. Same way.
Yeah, it works exactly the same way. Because as the consumer, you're just invoking methods through the interface and through the public API. You're not casting to the implementation type. There's a second question up here somewhere.
Is there any tooling to detect whether you have requires relations that are no longer valid? Say module A requires module B, and by refactoring I no longer require it. Is there any tooling?
There's no tooling yet. Great idea, though.
Right. So yeah. So if for those who mightn't have heard the question is there any tooling to support where I've got some redundant requires? So I've done some refactoring on the other module that I used to require I no longer need it. You can use actually JDIPs to help with that kind of thing.
Yeah, although it doesn't specifically look for that, but
No,
you
it
could
doesn't.
diff its output.
Yes, exactly.
But yeah, ultimately we're counting on the IDEs and other tools to provide a bunch of stuff like that. We did JDEPs for a couple of reasons. One is we need it, and the other is we wanted people to be able to get at a tool like that early on to be able to evaluate what it would take to move to 9.
But there's lots of opportunities to create plugins for Maven and other tools for this
Hey
kind of
kids,
thing.
let's do a startup. Any
Any
other
other?
questions? Okay,
All right. How are we doing on time?
92 minutes.
Okay. Okay, I want to get into start showing some of the command line options on how modules are compiled, packaged, and run. I'm going to stick with the examples I've been working through for the last couple of slides. So the first module that we will attempt to compile is stats core. You'll see quite a few new command line options in here, but just bear with it. The important thing when you're compiling a module is that you have what's on the left-hand side, which your source file get compiled to class files on the output on the right-hand side. It works exactly the same with modules, except this time we've got a module info.java that gets compiled to a module info.class on the output or right-hand side. So the javac command I'm using here, I'm giving it two options. One is the module path, and for this example, remember that stats core depends on Guava, so we'll assume that we've got a packaged version of the Guava module in the mlib directory, and I'm giving it this is a directory that I'm giving to the module path option, and that's where it will find the Guava module. The -d is the output directory for Java. That when you specify to javac, that's where the class files will go. And by convention, I'm going to compile my modules into the mods directory, mods / the name of the module. The source files that I'm going to compile are the module info and all of the source files that are in my stats core module. So they will get compiled from .java into .class files in the output directory, and the output directory in this case is mod / stats core. Now the module path, we've mentioned this in the linker command earlier on. I've now used it in the javac command. What is a module path? It's not like a class. It's not a class path. It doesn't suffer the problems of the class path. The module path is, just think of it as a sequence of directories for now. When you want to go and find a module, when I want to go and find the Guava module, I will search in the first directory. If it's not there, I'll search in the second directory. If it's not there, I'll search in the third directory. So it's a path for searching purposes. But once a module is found, it will no longer attempt to find that module in any of the subsequent directories. It's also robust in that if I put different versions of Guava into the same directory, the system will refuse it and say, this is ambiguous, I can't tell which version of Guava you're looking for. There's two versions of Guava packaged up into different jar files in the same directory. It avoids problems like split packages. I can't have two modules that are trying to be in the same, trying to share the same package. None of the problems that you have with the class path exist with this module path. It's much improved. So for these slides, assume the module path is where I'm going to find modules. All the tools, linker, Java launcher, compiler, they all accept the module path option. I compiled my stats core module into the mods directory. I'm now going to compile the stats CLI module. Remember, the stats CLI depends on or requires stats core. So similar javac command. I'm giving it the module path to where it will find the modules, and I'm giving it an output directory. The output directory in this case is mod / stats CLI. That's where it will compile the class files for stats CLI. As before, we go from source files to class files on the output side. Now we've got our two modules compiled, and we've assumed that we've all previously compiled Guava. I'm now going to run this module. So I'm going to run the CLI module, and we'll see what happens. I'm also giving the Java launcher the module path option, and I'm giving it a new option, -m, which is the main module. Oh, I see this has been truncated. Oh, I see what's happened here. 2 seconds. A new line has ended up in the middle of this. Now, that's that fixed in real time. The value to -m consists of two parts, the initial module and the main class. This will initially look a very verbose command line option. We'll shrink it as we move on to packaging in a few minutes. So what's happening here is that the system will have to is being told to run the stats CLI module, and this is the main class in the stats CLI module. Where is it going to find the stats CLI module? It's going to find it on the module path. The module path I've given to this command consists of two directories. the mods directory where I compiled my modules a few minutes ago, and the mlib directory, which is where we had guava a few minutes ago. So this just runs. So let me show you what happens when you type a command like this. So the first thing is the stat CLI module will be located. And the stat CLI module depends on stats core, it depends on Java base, and it depends on Java SQL. Java base and Java SQL will be found in the runtime image. Stats core will be found on the module path. So when you run this command, what happens is we actually compute the transitive closure. So all of their dependencies will actually be found to ensure that there's nothing missing. So we end up with this dependency graph. We'll overlay then the additional edges that are induced by the requires transitive or implied readability, and we end up with this readability graph exactly as we did earlier on. This happens when you type java-m stat CLI. If you want to see more detail as to what's going on, there's a debugging option on the Java launcher, xdag:resolver for resolver diagnostics. And you get some tracing information as modules are found, where they're found, what they depend on, and then a summary of the modules that were resolved at startup. This is all very, very simple, but it happens when you run this java-m to run a module. So that's compiling, that's running. Oh, I see a question at the back. Okay, so the question is, does everything get eagerly loaded? Not exactly. It's eagerly located here. There's no types from any of these modules loaded until they're all loaded lazily. Okay, so the question is there's two of these modules have types in the same package, and which one of them get picked, I think is what you're saying. Well, this cannot happen in these examples. If there's two modules with with types in the same package, then that get resolved, then the system will refuse to start up.
If they have a relationship to each other. If they don't, and if they're in different class loaders, then it could still work.
Right. Although everything here we're command line, it's all there's only one class loader involved here. There's you can't have two modules with types in the same package defined to the same loader. We'll get into a lot of this in the under the hood later on if you want to get into some of the details around that. But
The package of the main class must be exported to be executed.
okay, actually, a really good question. Is just the main class? Does the package of the main class need to be exported in order to be launched like this? No, it doesn't. I'm sorry. Sorry, we can't hear you. You would mind?
There's a mic right there.
Yeah.
If you want to try that?
Yes.
I don't know if it's working. You speak about J-Link or G-Link at the top of the presentation. Can I just launch it on, for example, my module with the main classes, and it's going to create the subset I need? Or do I have to find the subset manually and give it to him?
Okay, so I think what you're asking is when you give a list of modules to J-Link, does it figure out all the dependencies, or do you have to tell? No, J-Link will actually compute the transitive closure exactly like you're seeing on this slide at launch time. And in a few minutes, I have a slide which actually uses J-Link to put the stat CLI module into its own runtime image, and you'll see the modules that get included. All right, can I move on? Packaging. I've done compilation, done running. Now, when I've compiled everything here, everything's exploded on the file system. That's not a very convenient way to ship things. So I want to talk a little bit about packaging and putting your modules into jar files, or modular jar files, as we will call them. So you can package up your class files into a jar file exactly as you've done with libraries for forever. The interesting thing this time is if a jar file has a module.info.class in the top level directory, it is a modular jar. That means it can be used as a module on the module path. Another interesting property about modular jars is that if you deploy a modular jar on the class path, then the module info will be ignored, which ties a little bit to what we were talking about in the previous presentation with creating libraries that you want to run on 7, 8, and 9. So it's possible with modular jars to produce a library that just works on the class path with 7, 8, and 9, or it can work as a module deployed on the module path with 9. That's a little detail for later. So the jar tool itself, I can produce my module with the jar-create option. So the jar tool has been very revamped in 9 with a whole bunch of new options. You'll see a lot of double dashes in the commands that I show you here, and that's because we've started to use GNU-style options in many of the tools. There's actually a JEP that provides all the guidelines now for command line tools for the JDK. In this example, I'm creating a jar file called statscli.jar, and it's been created in the mlib directory. As part of creating the jar file, I'm giving it the location where the class files are, so it's --C, the directory where the class files are, and what classes to produce. This is exactly as jar has always worked. I suppose the new thing is just the main class. There's a more verbose way to specify the main class --main class, and I can give it the main class when I'm creating my modular jar. So all I've ended up with now is a jar file that contains all my class files. While I'm at it, I'm going to show you another option on the jar tool, which is print module descriptor. It's a short form of this. I realize this is quite a verbose command line option. And that allows you to describe a module or jar and print out its name, what its dependencies are, what its exports are. Very, very useful if you get a jar file and you want to know what's in it. So now we've got our modular jar. Let's just run it, and this time we've got a much shortened command line. I've given it my module path as before, but this time it's going to locate the packaged module rather than the exploded module. Exploded module is just all the class files on the file system. So my command line has actually shrunk a little bit now. I'm no longer needing to specify the main class. When I ran this a few minutes ago, I had to specify 2 values to -m, the initial module and the main class. Now the initial module knows what its main class is. I only need to specify the module name to -m, which is nice. So I've been using the module path for the last couple of slides. One thing I want to get across is that the class path has not gone away, and it's possible to mix the class path and the module path together. This is sort of somewhat of an advanced topic, but it's important for migration purpose to understand that you can mix modules and the class path. And for the example, I'm going to have another consumer of the stats library, the stats GUI library, and I'm going to leave that on the class path. So assume that our stats core and our stats CLI are modules, but I've also got a graphical user interface for doing statistics, but I'm going to leave it on the class path. So for this slide, orange is jar file on the class path. The hollow boxes are modules that I will be either on the module path or in the runtime image. So let's look at the command that mixes the class path and the module path. And this is what it looks like. Java --module path mlib, that's where I'll find the modules. --add module stats core -jar stats GUI.jar. So this looks a little bit complicated, but let me explain what's going on here. If I were to do java -jar stats GUI, I'm using an executable jar, and I'm going to execute the code that's starting with the main class configured in that jar file. There is nothing in that jar file that indicates what it depends on. There's nothing in there that says that it depends on the stats core module. So I have to help the system by using the add modules option to tell it that I want to resolve the stats core module, because I'm running something on the class path that does not know anything about its dependencies. The stats GUI module, or sorry, stats GUI application has a dependency on a whole bunch of system modules like Java Desktop. But you get those for free. They are resolved by the system by default. However, modules that are outside of the runtime image, you have to help the system with the add modules option to tell it what additional modules you want to resolve, because there's nothing in the main application to indicate what it depends on. Remember, my directory, my module path may have directories of thousands of modules. I don't want to have to go and locate all of those modules. I only want to locate the modules that are needed by the application, and that's why the add modules is there. Now I'll get on to linking. So there was a question up there about whether we could actually link in the stats CLI and what modules would get linked in if I were to do that, and do I have to tell it all its dependencies? So let's look at the JLink command. So this is very similar to the JLink command I showed earlier on in the presentation, except this time I'm creating a runtime image with my own application module. My same three options to JLink: the module path where it's going to locate the modules that I would like to include. So I've asked it to add in one module, stats CLI, and third option then is the location of the runtime image that will be generated by the JLink tool. JLink takes the stats CLI module, resolves it, computes the transitive closure exactly as you saw in with the Java launcher. So when I do a list modules to see what modules have been included in that runtime image, then I see, is it 7 modules here? Stats CLI, because I asked it to include stats CLI. Stats CLI depends on stats core. It also depends on stats. Or how's that? We had this. Stats CLI depends on stats core. We had a dependency on Java SQL. Java SQL depends on Java logging. Java SQL depends on Java XML. And stats core also depended on Guava. So that's how we ended up with the transitive closure. These 7 modules were included into the runtime image. And I could actually just do a java-m stats CLI, and it will run stats CLI application without specifying any module path this time, because everything is in the runtime image. I don't need to tell the system anything about any other locations from where to locate modules. All right, so this is a wrap-up of the intro session. It's very much introduce you to the basic concepts. It's important to understand the dependencies and readability, exports, combine them together to understand how accessibility works. And the second part of the presentation is the command line options. So you've got a flavor for what is involved in compiling a module, running a module, and also packaging and linking. So hopefully that's useful to give you an introduction to modules. The same link as we had before. We're developing the module system in Project Jigsaw and OpenJDK. This is the links to the project page where there's all the documentation on everything that we're working on for the module system, the mailing list, and where the early access builds are. Okay, any more questions? Is now. Oh, sorry, there's someone up there. Okay, so the question is, why do I have to verbosely add the JDK module? So you mean to the add modules option? Okay, so right. Okay, I see what your point is you're asking why did JLink need to be told where the JDK modules are? And the reason for that is that it needs to be able to locate those JDK modules in order to produce the runtime image. I might be on the Mac system producing a runtime image for Linux. I might be on Linux producing a runtime image for, I don't know, some ARM or some embedded platform. So the modules that go into the target image are not necessarily the same modules that I'm running JLink on.
Yeah.
What is the
Okay, so the question is about the state of the tooling and the IDs and Maven and Gradle and whether they have support for modules yet. I think it's still early days. If you download NetBeans or Eclipse today, they've got early versions of being able to produce modules. They understand module info and module packages. I see, is that Robert sitting over there? Do you want to come up here for a second to give Robert Schulte is one of the looks after Maven. Do we have a separate microphone? Just maybe you could give Robert can give a talk last night, but he can give a quick overview on where Maven is at.
So, about 10 days ago, I think, we released the Maven compiler plugin, version 3.6.0, and that one is capable to compile Java 9 projects, so include the module info file. One of the questions I got yesterday is, in these examples, you will always see the name of the module in front of the package. That's not necessary with the Maven compiler plugin. So you can just add the module info to the source main Java directory. So that's right now the news, I think.
I think in general, the changes in JDK 9 and moving to modules means it's going to take some time for all of the tooling to actually catch up. It's quite a disruptive change. New ways of building applications, new ways of packaging applications. It's going to take a while.
Earlier you said that the jar format is old and is not performant, so you plan to change it for JDK modules. And is it planned to do that also for user-built modules to replace DIP format with something else?
Okay, so the question is in the previous presentation I talked about within the JDK runtime image we've moved away from the zip and jar format to an internal proprietary format, and the question is whether we will do something similar for user modules. No, jar files are just too pervasive out there. We're not going to change anything now. We do have another format, a packaging format called JMod that JDK 9 supports. Which is it's not an executable format. It's a way to package a module with native code, configuration, binary launchers. In fact, the question was asked about where the JDK modules come from. We package all of the JDK modules in this JMod format for linking purposes. So the linker is the primary consumer of that format at the moment. But to your question is, we're not proposing that an alternative format for jars. They're just going to live forever.
I don't know that I would quite say never. It's certainly not in current plan. Our initial intent is that the internal JImage format is internal. We want to get experience with it. It's highly optimized. Lots of bit twiddling went into it to make it really, really fast for what it does. Maybe with experience in a couple few releases, we'll think about turning it into something standard that everybody can use, but right now we want to get more experience with it. And as Alan said, jar files are pervasive. They're a stupid format, but easy to understand.
Will there be a way to access the content via API?
Will there be a way to access the content by API? In fact, there already is. Part of JEP 220, thank you. When we took away rt.jar, we realized, well, hey, there are all these tools that access rt.jar and tools.jar and all this other stuff. So we provided a standard way through a NIO file system provider. And in fact, in order to get to this from, if you're writing a tool that needs to run on both 9 and earlier releases, what you can do is you can just look to see if the JDK you're trying to support has a file called jrt-fs.jar in its root, although we might move that, and then load that up with a class loader, and you'll find an IO file system provider, and you can use that file system to explore the content of this JImage file without having to know anything about its actual format. And we can change the format, and it'll keep working.
And I mentioned earlier about the IDEs already have some early support for 9. They're actually using exactly that API. That's how they actually access the class files in the runtime image.
Question about the
So the question is about the output of JLink. Does it have any jar files in it? No, there are no jar files in it.
Yeah.
The output of JLink looks a lot like the JDK that you download. It just is missing stuff.
If you
So
might
it's
remember,
got a bin directory, it's got a conf directory, all the usual things.
yeah, if you were around for the earlier presentation, I showed the layout of the runtime image. I can dig out that slide again if you want to.
Any other questions? Okay, shall we take a short break? We've got about an hour left, so...
Yeah, we do the advanced talk. Thanks,
10
Robert.
Yeah, thank you, Robert. We'll come back in 10 minutes at 3:35. Thank you. Okay, welcome back. A couple of minutes late, but that's all right. All right, here we are with advanced modular development. This is the third of the 4 sessions that we have. Looking at the time, my prediction is this will be the last one for this session. So if you want to hear the under the hood material, then you can come to that session on Thursday. Okay, this talk has 2 parts. One is about migrating applications. The other is about migrating libraries. And the first part I will do, and then the second part Alan will do. And that way we can refer to what we think the other is doing and see what we get wrong. At heart, a typical Java application has 3 layers. At the top are the jar files that you write. At the bottom is the JDK. And in the middle of this sandwich is sort of the filling. It's a bunch of jars downloaded from the internet by Maven or Gradle or whatever you use, and thrown on the class path where we hope for the best, and it all just works, right? Well, sometimes. In Project Jigsaw, we've turned the JDK into a collection of modules, such as, at the bottom here, we've got the base module, Java logging, Java SQL, Java XML, things you've seen in some of the slides we've shown earlier. 2 main benefits of modules, and you'll hear this over and over again, are strong encapsulation, so that no one outside can access its internals, and reliable configuration, so a module knows what it needs, and there's no need to go set up a class path. It can all be done for you. If this sounds good, you might be wondering how to turn your application into modules. Let's put some names on these jars, the blue ones, to get started. Let's assume the main application is myapp.jar, and it has some helper code in mylib.jar. And we'll assume further that that big cloud sandwich filling of third-party jars can be simplified to just Jackson, the JSON processing library. Jackson comes as 3 jars. There's core and data bind and annotations. To run the application today, you have to make sure the class path is set up like this, and that works. You wouldn't have to bother with that if myapp.jar and mylib.jar were actually modules, as shown here. Turning each jar into its own module is a fairly natural way to proceed. It's not always possible, especially if the jars have cyclic dependencies amongst their classes, which does sometimes happen. But let's go with that for now. Whenever you see a module, you should ask, what does it require and what does it export? Let's ask that for each of our prospective modules, myapp and mylib. One way to find out what a module might require is to run jdeps on its jar file, the jar file that you've already got. Alan mentioned this tool already earlier. It's a tool in JDK 8. It's been updated in JDK 9. Analyzes classes in jar files and finds whatever classes they refer to in other jar files or classes inside the platform itself. This slide shows the results of running jdeps on myapp.jar and mylib.jar. The classes of myapp.jar make use of classes in Jackson Core and Jackson Databind, and also, of course, in mylib.jar. Plus, myapp.jar uses classes from the base module, such as JavaLang object and JavaLang string, and it also uses some stuff in the SQL module. Mylib.jar only gets 1 line at the very bottom because it just uses java.base, so that's nice and simple. With this knowledge, we can write module declarations for these jar files. Here's the module info.java file for mylib. All it requires is java.base. Now, we don't actually need to write that. As Alan mentioned, the compiler will insert that for you automatically. You don't actually have to, but if it makes you feel better, you can. Now, JDEPs can't realistically help you with exports. So let's say that my app exports a package called com.myapp.lib.util. to the myapp module that we're going to make. This is a qualified export because it's specific about which other modules can access that package. Not any module can access that package, just a module called myapp. Now let's turn to the moduleInfo.java file for myapp itself. It requires mylib, the module we just created, and JavaBase and JavaSQL. And of course, we know it's going to use Jackson, so we'd like to write requires jackson.core and requires jackson.databind. Does that mean we have to write module info files for them too? Well, that would be a pain, especially if we don't happen to be the maintainers of Jackson. I mean, you could do that, but ew. If only there was some way for Jackson jar files to somehow become modules automatically. Then we could write the moduleInfo.java file for myapp like this. Very simple. Requires jackson.core, requires jackson.databind. We'd have a beautiful module graph with myapp depending on mylib and Jackson core and Jackson databind, and also on JavaBase and JavaSQL. Indeed, there is a notion of automatic modules in the module system. An automatic module is a jar file that you put on the module path rather than the class path. Once you do that, you have a real module. You don't have to make changes to someone else's jar file. The module name is derived from the jar file name, so it's predictable. It exports all of its packages, since we can't tell any better, and it requires all of the modules, because it might be using anything that's actually available. In effect, automatic modules mean that today's jars are tomorrow's modules. There are some limitations. The automatic modules can't have conflicting packages and classes and things like that. Once automatic modules spring into existence for Jackson Core, Jackson Databind, and Jackson Annotations, the module graph looks quite different. There are quite a few more edges here. That's because the automatic modules basically require everything. They require each other and all the modules in the JDK image and all of your modules as well. This is to provide the maximum possible compatibility surface area for code in those jar files. You might think that the module system could run JDEPs on the automatic modules at startup and try to figure out what modules they require. Not only would that take time, but it wouldn't really help, it turns out. The reason is that libraries you find in the filling of the sandwich often make use of core reflection, the Java Lang Reflect API, to inspect classes dynamically. JDEPs can see the use of core reflection, but it can't figure out automatically what classes will be inspected because in general those class names are computed at runtime. In fact, the Jackson Databind module does exactly the same thing. When code in myapp calls the Jackson API, it passes its own class object. The intent is that Jackson Databind can create an instance of, say, the myValue class as shown here. But this won't succeed because we never got around to saying what myapp exports. It doesn't really have an API. It's the application. It doesn't export an API that's supported in any way. But it needs to export some packages anyhow for this reflective purpose, and you might well find the same thing in your own application code. The solution is to declare that myapp is what's called an open module. An open module opens all of its packages in a way that allows a framework like Jackson.databind to reflect over its internals. In effect, you get the benefit of reliable dependencies, but without the full power of strong encapsulation. Frameworks that reflect over application code are a total reality in everyday Java development. They're not going away anytime soon. It's a usage model that's important to support going forward. So application code can't always be strongly encapsulated, and that's fine when there's a good reason not to do so. We think that the open modifier is a clear statement about the nature of this module. It's open for deep reflection. Without the open modifier, a module is strong. It explicitly defines an API via exports clauses and is not intended to be deeply reflected upon by frameworks, unless in a strong module you can actually open individual packages by hand if you really want to. Let's come back to the overall module graph. It is pretty messy, but it's better than when everything was a jar on the class path. For example, there's no arrow from mylib to myapp, so there's no danger of code in mylib accidentally reaching into myapp's internals or becoming dependent upon some class in myapp. On the class path, code in mylib.jar could access code in myapp.jar quite easily, and that's what causes maintenance headaches down the road. In fact, if you think about it, the class path is pretty crazy. With just 10 jars, you get 100 possible ways for code to interact. Who knows what's going to happen? The class path, in a way, is the ultimate in erasure. People complain about erasure in generics. Erasure on the class path is way worse. Whatever you know about the structure of your system, the class path throws it away and connects everything to everything else because, well, it might be necessary and it doesn't know any better. This means conflicting classes and missing classes and generally slow lookup every time the virtual machine needs to read a class, which, gee, is kind of pretty often. With modules, you're telling the compiler and the VM what you know about the structure of your system, and finally, they're paying attention. Speaking of the compiler, let's see how you run it. We've got the Jackson jar files in the lib directory here. We treat them as automatic modules by putting them on the module path. We have the myapp and mylib source in the source directory. We tell javac about this with the new module source path option. This is necessary because there's a new level in the directory hierarchy when we're compiling modules. You have source and then the module directory for the module name, and then the module info.java and the whole traditional package hierarchy. The result, the output of the compiler, is class files in the mods directory. We run jar to build mylib.jar based on the classes in mylib, and then we run jar to build myapp.jar from the classes in mods myapp. We also specify its main class so that we don't have to type it later on. Because the jar files have modulinfo.class files, we call them modular jars. And there's a cool trick about modular jars. If you compile the class files for 8 and the module info for 9, then you can actually take that jar file and run it on 8. Java 8 will just ignore the module info.class, and as long as you're only using 8 APIs, it'll still work. Now, you can run your modularized application with this much simpler command line. All the stuff from the class path is now wrapped up in the module info.class files. Remember, the explicit modules are located in mlib, and the automatic Jackson modules are located in the lib directory. So to recap, first we built modular jar files for our own code by writing and compiling modulinfo.java files. Then we created automatic modules for third-party code simply by putting those jar files on the module path without change. If you like, you can think about this process I've just described as top-down migration. That should make you wonder, is there also bottom-up migration? And indeed, there is. Here's Alan to explain that.
This is actually my favorite part of the talk because I get to tell you that to ignore everything that Mark said in the first half of the talk. So this is library migration. So I'll go back to the slide that Mark had earlier on, and for this part of the presentation, we will assume that we are the maintainers of the sandwich, or the filling of the sandwich, and we're the maintainers of the Jackson libraries. So our goal in this part of the presentation is to convert the Jackson core, Jackson data bind, and Jackson annotations into explicit modules. So this is from the bottom up. We've already got our green platform modules at the bottom, and I want to turn these into nice, clean, green modules. 3 modules. So orange is class path, green is modules. So by the way, for this we will assume that what's in these jar files are actually good candidates to be modules. I'll not get into some of the details about that. But exactly as before, anytime that you actually meet a module, you ask it the 2 questions. What does it require? What does it export? We've got 3 modules, so we have 6 questions to go and ask because it's 3 modules. So I'm now going to go and write a module.info.class and convert each one of these jar files into an explicit module. One of the useful things we have with the JDEPS tool is that it can generate you a module info. Sorry, first thing we want to do is see what is the dependencies between these jar files, and I will use JDEPS to do this with the JDEPS-S option to give me a summary of what its dependencies are. So like Mark did previously, I'm going to run JDEPS-S on the Jackson jar files to understand the relationship between them. Jackson annotations jar file only depends on Java base. Jackson core only depends on Java base. Jackson data bind is a lot more interesting. It depends on the Jackson data bind. Sorry, it depends on the Jackson annotation and the Jackson core. It also depends on a couple of platform modules: Java Base, of course, Java SQL, and Java XML. So this is interesting because now we can actually draw a module graph and understand the relationship between these modules. So this is the dependency graph. Jackson data bind at the top, depending on Jackson data core and Jackson annotations, and then the dotted lines around the platform modules. I'm now going to write the module info. I thought I was doing that a few seconds ago, but I'm going to write the module info for each one of these 3 jar files. And another trick up the JDEPS tool is that you can use the dependency information that JDEPS can determine by static analysis to produce an initial module info source file that you can then edit to make it the actual module declaration for the module. And the JDEPS option that does this is gen module info. So JDEPS --gen -module -info. I give it a directory where I'm going to generate these source files, and then the list of jar files or class path of jar files that I'd like it to analyze. So from my 3 jar files, it will produce 3 module. It will generate 3 module info.class files, and we'll start looking at these to understand what it actually produces. So this is the module info that JDEPS will produce for or generate for the Java data bind module. JDEPS does not know anything about what packages should be exported. So what it does is it generates an exports clause for every single package for where there's types in the jar file. With the dependency information, it can generate the appropriate requires clauses. It can even be smarter in that it understands the API signatures and which types of other modules appear in a module's API. So it can produce the requires transitive. It can generate the transitive modifier when needed. So when I look at this example, we will see that there are so Jackson data bind requires transitive Jackson core. I can tell immediately from this that there is something in the Jackson data bind API that has some types from Jackson core in the API. There may be parameters that are passed into some method on data bind. Maybe it's a return type from some method on some type in Jackson data bind. So this gives me a starting module info.class that I will now edit to make it the right module declaration. So assuming we're the maintainers of Jackson, we will have a lot more deeper knowledge of that library and which packages should be exported. When I scan down through these list of packages, there's a few suspicious ones in there, particularly the .impl. So I can see dsir.impl, jsontype.impl, sir.impl. We will assume for this that these are internal implementation types in those packages, not supported part of the API. So one of the things I will do when I edit this module info, I will delete those lines. Now, if we were really the maintainers of Jackson libraries, then we will have a lot more insight, and maybe we will come up with a slightly different set of exports. But for now, assume that anything impl is not part of the API, so it should not be exported. We'll leave the requires as generated by JDEPS because they look right. Now I'm going to compile my 3 modules. I'm also going to use multi-module compilation and the module source path option, which is the way I'm going to compile all 3 of my modules with one javac command. My source code is laid out for this compilation, src/ the module name, and then all of the source files for the module are in that tree. So one javac command, the module source path, which is the root directory where it's going to find the source of all of the modules, and then I'm going to compile every Java file that it finds in that tree. I'm now going to package up my 3 modules. So I've compiled all of my modules. There's now in the mods directory, I've got 3 directories with all of the exploded class files, and I'm now going to run the jar command and create a modular jar for each one of the Jackson modules. So it's the same Java command and jar command that we used in the previous deck, dash dash create, give it the name of the jar file with dash dash file. I'm using the opportunity here to add a module version to the module as part of packaging. The module system itself does not know anything about versions, but it provides a way you to add a version string at packaging time, which is very useful for diagnostic purposes. So now what I've ended up with is an mlib directory with 3 jar files in it. Jackson core jar file, Jackson databind.jar, Jackson annotations.jar. And this is what the resulting module graph is. So it's a nice clean module graph. The dependencies are very clear, modules from the bottom up. Platform modules at the beginning, our Jackson modules in the middle, and I've left the application on the class path in orange, myapp and mylib. This is the command that we had right at the start to run this, everything on the class path. We no longer have Jackson core databind and annotations on the class path, so we'll remove those, and this is the command that we've ended up with now. It looks a little bit complicated because we've got both a module path and a class path, but let's work through this. So in order to run this application, I'm giving it a module path where it's going to find the Jackson modules, and I'm giving it a class path with myapp and mylib because they are on the class path. And the name of the entry point or the main class on this application is myapp.main, so that's why I'm specifying this. So one other thing that's in this, and we had this in the intro earlier on when I showed how you mix the module path and the class path, I have to use add modules. The reason is there's nothing in myapp.jar that indicates that it has a dependency on Jackson databind or any of the other Jackson modules. So I have to give it the add modules option to tell the launcher that I now want to resolve the Jackson databind module, because there could be 1,000 modules packaged up into different jar files in mlib, and we need to tell the system you need to resolve the Jackson databind module. So that is how you run with the class path and the module path. In this case, Jackson is modularized, and we've ended up with this nice module graph, and this is modules from the bottom up and the application remaining on the class path in orange. Now I want to start putting things together. The first part of the presentation, Mark modularized the myapp and mylib. Where we've got to in the second part of the presentation is from the bottom is the middle tier of jar files. The sandwich has been converted into modules. Now I bring in Mark's modules, myapp and mylib, and we end up with a nice clean module graph. So there's modules all the way up from the bottom through the platform modules, the filling in the sandwich, and the application and its helper library mylib are all modules. So now let's go and run that and see how it looks. So the first thing is assume that all of the jar files, both the myapp, mylib, the 3 Jackson modules, they're all in the mlib directory as modular jars. The command to run this is a lot simpler now. I give it the module path as before. This is where you find the modules. They're in the mlib directory. And I do java-m myapp, which is the initial module. It knows what its main class is. Myapp will just run. Its dependencies are clear from its declaration, and all of the dependencies will be found in modules in the mlib directory or in the system image. So it's a nice, simple command line. Now let's move on further, and we'll start to link these together. And we use the linker tool that we used earlier on. So the linker command, I'm going to, this is the advanced talk, so I'm going to use some advanced options on the linker. But as before, when you run the linker, you give it the module path. Where do you find your modules? What modules do you want linked in? Where do you want the runtime image generated? But because this is an advanced talk, I'm including some interesting options to do some compression and stripping in order to actually generate a much smaller runtime image. So the module that I'm specifying to add mods in this command is myapp. Myapp depends on mylib. Myapp depends on Jackson databind. Jackson databind depends on Jackson core, depends on Jackson annotations. All of these modules will get linked in. And let's see what the resulting image size is. In this case, it comes out just around 26,000. It's just about 25 and a half megabytes of a runtime image, which is all of these modules, which is actually quite good. When I look in the bin directory, I can see that the Java launcher is in there, and there's also a special launcher generated for my app. We'll have a look at that in a few minutes. And if I do a list modules to see what modules are in this runtime image, then I see my app and my lib. I see the Jackson data mine modules, and I see the 4 platform modules that are transitively required by the Jackson and my app. So I've ended up with 4, 7, 9 modules in this runtime image, which is actually quite nice. Now let's run this. And now my command has really shrunk. If our goal was to get to a small command line option, then this is probably as small as it gets. So with this runtime image I've generated, I've just done java-m my app, and it runs my application, and it will resolve at startup the Jackson modules and the platform modules that it needs. So that's really, really nice. But I can actually do better. When I looked in the bin directory in the last slide, you saw that there's actually a my app launcher generated by the JLink tool, and this will actually make it smaller again. So instead of me having to type java-m my app, I can actually just do bin/my app, and it'll run my application exactly the same way. So that is modules from the bottom up, and combining it then with modules that are migrated from the top down. The main thing with the module system is that it gives you the freedom to adopt modules at your own pace. That's actually very, very good. You can start with migrating your application and your own libraries to modules without waiting for everyone else to have migrated to modules first. You can migrate libraries independently to modules, which is really, really useful as well. And to combine together, it means you can do your migration at your own pace. In this presentation, you've actually got a flavor for a couple of you've actually got a flavor for all of the module types that are in the module system. When I type a module info.java, I'm actually creating an explicit module. I'm declaring my dependencies. I'm declaring my exports. If I take a jar file and I move it from the class path to the module path, and there's no module info in there, it's an automatic module. That's what Mark did in the first half of this presentation, where all the packages are exported. The module depends on everything else. That's an automatic module. There's no module info for that. You've also got a flavor, and we didn't go into much detail in this talk, is the proposal for open modules. So a module where I just declare its name with no other modifiers is what we call a normal modules. Everything's encapsulated unless exported. The open module that Mark showed for my app is one that can be deeply reflected on by frameworks out there. It's a kind of an advanced topic. So that gives you a flavor for the different types of modules. So summary on this is now that you know about migration from both the bottom up and the top down, is go forth and modulize. And that is the end of this deck. Same information, same links as we had on the previous deck is Project Jigsaw, where we develop the module system, mailing list, early access builds. So questions. Okay, one question to get started. Versioning. Yes.
What about it?
A couple of questions. With jar files, for example, your Jackson example, version 2.6.2, especially with transitive dependencies, I mean, you get version collisions, you get multi-version jars within your class path. Any way to deal with that through modules?
So that was partly a question, partly a comment. So, folks, there is a mic up here. It would save us a lot of time if you would use it. I know you have to get up, but especially with where there's a question that's preceded by a bunch of comments, which is a fine thing.
Versioning, especially with jar files now, it's all version dependent with transitive dependencies, different versions of the same project also happening. I just heard a remark, versions or modules are not version aware.
they can have version information for debugging purposes, etc. If modules are a way to move away from jar files, or are they? Is there any way to deal with multiple versions, saying I need to be dependent on at least version this of this module?
Yes, you can say that in your POM, or in your Gradle build file, or in whatever other build system you use. So part of what's going on here is we did a little sidestep away from a really, really hard problem. A really, really hard problem that other tools have already solved. Maybe they haven't solved it optimally, but they've solved it well enough, and maybe in future they'll get better, or other tools will come along that are better, or who knows. So I like to tell a little story in response to this kind of question. In the first prototypes of Jigsaw, which of course are now some years ago, we actually did version selection. In a module declaration, you could write requires foo, greater than 1.2.3 and less than 5.9.0, and so forth. And in general, doing resolution in the presence of constraints like that is an NP hard problem. So to do it really well, we were actually on the verge of merging in a copy of a SAT solver, a thing called the SAT solver, high-end heuristics for solving Boolean satisfiability that can generate usually a near-optimal solution to these kinds of problems. And around that time, we were also thinking, well, how is this module system going to interact with existing tools? Because it would be a non-starter if we said, okay, modules in Java 9, yay! Oh, you use Maven? No, you can't use Maven anymore. Use Eclipse? No, you can't use Eclipse anymore because they're doing all this module, all this version computation in a different way than we are. That wouldn't be very good. Or we could choose to bake into the Java platform standard the exact set of heuristics that Maven uses, but then the Gradle people would be unhappy. And it's just basically it was a problem that we didn't need to solve, so we didn't solve it. If you need version constraints of that form, they're properly the domain of your build system. Modules are in some sense a little, I don't know, they're a little more platonically essential than what the build system deals with.
Okay, thanks.
Mm-hmm.
Is it possible to do wildcard exports in the module file? So suppose you, like for example in a jar, you have 2 packages, and under those packages you have a lot of sub-packages, and you grow those organically?
No.
Okay.
No, our view is that exporting a package as an API should always be an intentional act that you think about, rather than something that could happen accidentally because you put a wildcard in one day and then a month later you added another package and it turns out, well, that was meant to be internal, but now it's not, and then it just becomes a mess later on. So you can make an entire module open because it's okay to say, okay, well, this module, it's just full of 5 packages full of Pojo classes. I want them all open for deep reflection, but don't export any of them for API at compile time, and that's fine. But there's no equivalent of a way of saying that a module has every package exported no matter what.
In an earlier spec, you also had the module keyword, and you could say on the Java classes themselves that this particular method is exported.
That was on a way earlier spec. That was like JSR 294 or something.
294, yeah.
Probably more than 10 years ago. That is long. That water is so far into the bridge. I mean, it's gone through the evaporation cycle 3 times already.
Is there any chance it
No.
might come in future versions?
Highly unlikely. For those of us on the work on the JDK, we often find ourselves in the position of, well, if this were 1995 and we were designing Java from scratch, yeah, maybe we would do it that way. But the main reason we rejected that approach is it would make migration horribly difficult. If you wanted to migrate an existing component to be a module, right now we've come up with this design where, well, you write, everything goes in that module info.java file. You don't need to change any of your other source code. If you had to sprinkle the module keyword everywhere, then everything would have to change. It would be really hard, if not impossible, to ship the same artifact for multiple releases, and adoption would be much lower than what we're aiming for.
Thank you.
18 minutes left. If you're shy, you can ask questions on Twitter. I don't know if that helps. Tweet at Devox Jigsaw. I'll look for that. Go to the microphone, please, if you're in the room.
So, what about open modules and split packages? Are they allowed?
Sorry, how do they relate to each other? I mean, do you, if you have two open modules, can you suddenly allow split packages?
Yeah.
No. Good. Sorry.
I have one question. You showed one mailing list for the Open JDK.
Mm-hmm.
I saw on the web there are about 50 mailing lists. Why so many mailing lists?
50 mailing lists for Jigsaw? For the model system? No.
Oh, I bet you're looking at the OpenJDK page where there's a mailing list for each project and each...
I guess so. Yeah.
Yeah.
Oh, so
well, OpenJDK is a large community.
Yeah.
Jigsaw is just one project inside it.
Okay.
Right. There is more than there's actually more than one mailing list associated with this project. Jigsaw Dev is for discussions about the implementation and experiences with the prototype, and feedback on the EA builds and so forth. For the JSR, for the module system itself, there are 3 mailing lists, and they're JPMS-spec-experts, observers, and comments. But for everything we've talked about today, there are a total of only 4.
Okay. Thanks.
And they're reasonably well defined.
Just to make sure if I understand correctly how it works with the new modules, the command line is the only way how I can interact with the whole system, how to prepare the collection of the modules that the Java is supposed to pick. There's no API that helps me to build this after I have started the Java process, right?
But there is. Come to under the hood. There's what's visible on the command line in terms of setting up the module path, and the module graph is a subset of what you can actually do with the reflective API. There's an API concept called layers. Modules live in a layer. What you can do from the command line is arranging modules and class loaders in the boot layer, but you can make layers above that, and you can configure them pretty much however you want.
The second question is, how does the concept of a class loader relate to a module? Does every module have its own class loader that sees other class loaders?
Good question. Also another question that's answered in Under the Hood. The module system and class loaders are almost perfectly orthogonal. Right? The class loader API has hardly changed at all. If you have an existing system that does really sophisticated things with class loaders, you can probably merge modules into that kind of system fairly easily. We had to do that for the JDK itself, because it has, there are the 3 built-in class loaders. They've been built in since 1998. We can't change them, or every bit of code in the world will break. So it is not the case that every module has its own class loader. A class loader can have many modules in it, or it could just have one. All depends on what you want to do and what your needs are.
Thanks.
Well, there's a user called Devox Trump on Twitter. Open modules should be renamed to Trump modules. They protect the interface, but anybody can get in. Okay, whatever. Any other questions? 13 minutes on the clock. Well, we'll let you think for a minute. Or
So
do we?
is there really a Trump Devox?
Yeah, at Devox Trump. Make Devox great again, Antwerp, Belgium. I might know who this is. Glad to hear you can still use Corba in Java 9. My friend Devox Borat would approve this.
Question?
I always said Devox voting was rigged. Nobody believed me.
I have a question, small one.
Oh, sorry.
If you can explain a little bit about the layers, and is it possible, for example, two modules to have dependency on same library but with different versions in the same project?
I think I can answer both questions with the same answer. Or do you want to try this?
No, you go ahead.
You've been doing more talking today. Okay, so a layer is, I mean, you could think of it as a stack of pancakes or waffles or something, right? You have the boot layer that has the Bootstrap class loader and the what used to be called the system class loader, the platform class loader, are all in the boot layer. That's the stuff that you set up from the command line. You can make a layer on top of that. You can have modules in that layer. You can say when you configure that layer, you can tell it how to find the modules that are going to be in that layer and what modules you have to have, and it'll go do the transitive closure computation and figure out the module graph for that layer. The modules in this new layer can refer to modules in lower layers, and then you can make another layer on top of that. And every layer can have its own modules referring to each other and referring to stuff lower down. You can't refer back up.
They can also refer to different versions of the library?
Yes. So in two different layers, you could have two different versions of the same library. No problem.
So we can solve the dependency hell?
Well, so you can solve dependency hell as long as you're willing to play the layer game, right? So it's a little bit of a cost, but it simplifies the system immensely.
Okay, thanks.
Thursday talk has
Yep, under the hood has an entire section on the wonders of layers. And layers might seem like a really heavyweight concept, but actually they're really lightweight. So if you have to make lots of them, that's not necessarily a bad thing. A layer is really just an association between class loaders and runtime module objects, which are we've managed to make fairly inexpensive.
I presume, for example, the Reflection API had a lot of modifications for the module system. Is everything still backwards compatible on the deeper side of reflection and stuff like that, or there's
almost completely, but not quite.
Yeah. Well, I suppose the main change is you can't use a reflection API to break into types in non-exported packages or non-public types in exported packages. But
and related to that, there's this issue that is about which we occasionally hear various flamage. The set accessible method, which is what you need to use to break into a private member, it has always thrown a security exception if the security manager says, no, you can't do that. Well, now in 9, there's a new reason you can't do that, which is that the member is in a package that's not exported and not open. And so in that case, well, to be absurdly, perversely compatible, we could throw a security exception, but that would be stupid because most of the time there is no security manager. So instead, we throw a new exception called inaccessible object exception. It's a runtime exception. The API signature didn't change. But there are some people in the world who have a very strong view that we should throw a security exception there instead, even when there's no security manager, because they have brittle code that can't deal with this new exception. So it's one of those difficult trade-offs where you try to do the right thing and old code breaks, and I think we're going to wait for some more data before we decide on what to do about that one.
One other thing about the reflective API is it has additions in there, like Java Lang Reflect module, which represents the runtime module and provides you APIs to be able to understand what the module is doing. A module can actually extend its readability graph and its exports of runtime. There's a lot of flexibility there.
Quick question, what's the current schedule for Java 9? What are the next steps?
I think you'll find that on the convenient JDK 9 project page. The current GA date is July 25th or 27th, something like that. Yep. So we're trying to wind down in the next few months. No questions on Twitter. Okay. Any more questions here, or they're just people leaving? Or people anxious to leave? All right. Well, let's call it a day. Thank you very much.
Thank you.